All right, so in this video, we're going to start to talk about the conservation of momentum. So the law of conservation of momentum is that momentum is always conserved. So remember that the equation for momentum is mv, and this is always conserved. Right? So let's do an example. We say that momentum is conserved in explosions. So I'm going to start with an explosion example, and I'm also going to talk about some examples of collisions in this video and in the next video. So let's say you have an object, and let's just do a conceptual example, and then we'll do an actual mathematical example. So let's say you have like a bomb, right? And so if it were going to explode, right, initially the bomb is just sitting there, it's at rest, and then it explodes and all of the pieces sort of fly off in every direction. So the question is, how is momentum conserved in this case if the initial velocity of the object is equal to 0, that means that the initial momentum of the entire object is equal to 0. But then you get all these parts and they're flying everywhere. So how does the initial momentum 0, but then you have a bunch of different parts that have a momentum? Well, the fact is that the momentum is conserved because we've got to remember that momentum is a vector, because velocity is a vector. So as these all move off in their opposite directions here, you can see that each one of these vectors would cancel out so that the net is 0. So let's do an example of like an explosion type problem. Now we're going to simplify it so we don't have to solve all the components of these things. We're always just going to have a very simple sort of problem. So what we're going to be doing in the lab is you're actually going to be taking two Pasco cars, and they're going to be sitting next to one another, and you're going to use the plunger in order to push them in opposite directions. So let's just say that one of the cars is 4 kilograms, which is not, and the other one is 6 kilograms. And initially they are at rest, and then you hit the plunger, and this one flies off in a direction, let's say to the left, that is 2 meters per second. And we want to know, okay, well, what does that mean about this guy's velocity? How fast is he going? Right? So what we need to know is we need to know that momentum is conserved. So we're going to think about what's happening before the scenario and then after the scenario. So before the scenario, we have a momentum equal to 0. We have a 4 kilogram mass that has a velocity of 0, and we have a 6 kilogram mass that has a velocity of 0. So those are both going to be 0, and they're going to equal 0 overall. Then in the next case, after the scenario, so I'm going to put that on the right hand, after the explosion happens, we have a 4 kilogram mass that's moving to the left at 2 meters per second. Let's just make the left a negative direction, right? So we have 4 kilograms, and we have negative 2 meters per second, and we have to add that to the velocity of 6 kilograms, or the mass of 6 kilograms times its velocity. Okay, so the total momentum here of the objects has to be equivalent of them here. Now these actually have to cancel out because the initial momentum was actually 0. So let's just solve for what that velocity is. So these, you'll end up, if we just simplify this, right, you're going to have 0 equals negative 8 plus 6 times v. Right? So we get that 8 is equal to 6v. So if I just take 8 and divide by 6, I get the velocity then to the right of the second car is 1.3 meters per second. So this velocity is 1.33 meters per second. Okay, and it's to the right. It's a positive value, so that's how I know that what the direction is, because I said that left was negative. All right, so that's a simple explosion problem. I'll leave it with that for this video, and in the next video I'll discuss elastic collisions.